This is OPTI 388, Lab 9, Diffraction. I'm Zeller.
I'm Sophia Centeno.
And I'm Ethan Luker, and our TA is Liaf.
This lab explores diffraction, the bending and interference of light through apertures to reveal wave behavior in optical systems. In Part A, we started by examining single and double slits, observing the transition from the Fresnel region, where near-field fringes shift and change form, to the Fraunhofer region, which shows the aperture's Fourier transform. Our setup used a laser diode, 3 lenses, an iris, a neutral density filter, an aperture holder, and a CCD camera connected to Thorlab's software. After aligning the beam, we captured 5 single slit images, from the sharp slit image through 3 Fresnel transitions to the Fraunhofer pattern, and repeated the process for the double slit. Sliding the lens camera assembly along the optical rail reveals how each pattern appeared at specific distances, showing how the setup determines the diffraction pattern.
Part 8 continued, triangle, square, and circle apertures. The goal was to see how diffraction changes from the Fresnel near field to the Fraunhofer far field. We did this by moving the camera and lens back and forth along the optical rail. When the camera and lens were closer to the apertures, we observed Fresnel diffraction patterns. We adjusted the iris and camera exposure to capture these images. As we moved the lens and camera further away, we saw the Fraunhofer diffraction patterns. These showed each aperture's Fourier transform, which were a triangle transform for the triangle, a 2D sinusoidal pattern for the square, and an airy disk for the circle. We adjusted the exposure to help us get clear peaks in our Fraunhofer intensity plots. This experiment showed that diffraction strongly depends on both distance and the geometry of our aperture. We confirmed that each shape produces a unique pattern tied directly to its Fourier transform.
This was Part B, beam profile measurements. In this part of the lab, we measured how a laser beam spreads or pitches as it travels. A Gaussian beam has its smallest width at the waist and gradually expands outward in a predictable way. The Rayleigh range marks where the beam begins to noticeably spread, and the divergence angle of the numerical aperture describe how quickly it expands. Together, these parameters define the shape and quality of the laser beam. We aligned a Henny laser along an optical rail with the beam profile connected to the computer. Beam width readings were then taken at multiple points along the rail in both the X and Y directions. These measurements were then fit to the quadratic equation shown on the previous slide to provide beam waist, its position, and how the width changes with distance. From this, we determined the beam's divergence and numerical aperture. The beam width increased smoothly with distance matching the expected Gaussian shape. The calculated waist and numerical aperture values were fairly consistent with the typical Henny laser output. This confirmed that the beam followed Gaussian behavior and showed that this method provides an accurate way to measure the laser divergence and optical quality.